Good morning, Dongting. How are you doing?
Fine.
Good evening, I guess, for you.
Yeah, yeah, evening.
So you have this class at night for you, and then you sleep, and then you have classes that are in the morning for you that are actually in the evening here.
Mm, yeah, for Thursday. Yeah, Thursday.
Okay. That's got to be complicated.
Yeah, but like after 4 weeks, it's
You're getting used to it?
yeah.
Good. Good morning, other people. Morning, Thomas.
Good morning.
Okay, well, it's time. I assume some other people will amble in as people amble, because it's morning on a Friday. Morning, Sophie. So again, so I've moved the whole collage thing and the following assignment both forward a whole week. So collage due next Friday. The thing after that's due 2 weeks from Friday, or 2 weeks from today. And we'll see how things go. But it's important, I think, that people understand what's happening. Oh, just a second, I'm gonna close the door. It's important that people understand what's happening. So I wanna sort of balance the schedule as best I can. I also want to encourage people to use office hours, appointment slots, things like that, to come and talk. Like if you're confused about things, one thing that I got from doing the what kind of questions do you have, and I think we should do more of those, was I think there were people that had just sort of general I'm confused vibes. And the best way to deal with that is to set up a meeting and let's talk one-on-one, because it's hard for me to provide good help in class when I just have like, I don't really understand pictures in some ways. And so definitely, you're paying my salary, sign up. Like, let's have a conversation. If my slots don't work, let me know. It's hard to make times that work for everybody who is in the class. And so, I do the best I can, but if the slots are bad, let me know and we'll try to like set something else up at a different time that works for you. But it's important for me to be able to help you out. So, based on the questions from Wednesday, I want to move to pictures today because we really need to get like doing some stuff with pictures or you're never going to get the collage thing done. And pictures are frankly fun. I mean, they're a cool thing in this class. And I think they're, for some of you, they might be an important part of why you even signed up for the class. So I want to like get to pictures, but I also want things to make sense. So my plan today was to go over a couple of examples from the book that people had raised questions about, but also try to create opportunities for you to step out for short periods of time into breakout rooms, try some things, and then come back and share maybe some pictures that you sort of fiddled with. Because that might be more fun than just like disappearing into groups and not talking to each other. Are there any questions about anything before I actually start?
For the collage assignment, do we have to use like 4 different photos, or can it be like all of the same photo?
It can be all the same photo. Like you can do it, you could take one photo and chop it up and lay out parts in different places. If that's what you want to do, or you can have totally different photos. It's entirely up to you. Does that make sense?
Yes. Thank you.
Not a problem. You know, thinking about it, it might be useful, and I wasn't prepared for this today, but let me make a note. Maybe Monday or over the weekend, I might just do it on Canvas. I should maybe share some examples, because that would maybe be helpful. Example collages. And if like one of them was all constructed out of the same image, then that would help answer your question, Thomas. But I think that would be a really useful thing to do. So let me actually plan on doing that. I will create and share some examples. I'll probably just share them, probably actually add them to the write-up of the assignment, to be honest with you. And then I'll post a note in announcements saying that I've updated the assignment so that it includes some examples. And then you could go have a look there. Does that seem like a good thing to do?
Indeed.
Okay. Other questions? That was a great question. Thank you. Going on. Gone. Okay. So I'm gonna share my Jess window. Share screen. Jess, share. Okay. So we're all looking at my Jess window, I assume. Is that somebody give me a thumbs up? Good job. Okay. So there was a question about sepia tint, which is in chapter 5, I think. And sepia tint uses as one of its actions the grayscale new program from chapter 4. And I love the grayscale stuff, actually. The grayscale stuff makes me very happy. As a photographer and somebody who likes playing with images, I find the grayscale stuff to be like super fun and interesting. And so having an excuse to go back and play with grayscale makes me happy. So we'll start with grayscale, then we'll get to the sepia example, and then I'll have you go and like play with that some, and then come back and maybe share some pictures. So that would be fun, I hope. So grayscale, we're trying to take a color picture and make it black and white. Okay, so the goal is to take a color picture and make it grayscale, which, you know, in colloquial terms is black and white. Of course, it's not really black and white. It's got all these grays in it, but we refer to black and white photography when what we really mean is grayscale photography. Now, what does it mean for an image to be black and white or grayscale? A picture is a shade, or a pixel, I meant to say. A pixel is a shade of gray if, spell it the way the book does, if all three of its color components, red, green, blue, are equal to each other. Right? So if we have something that's like 126, 126, 126 would be a medium shade of gray. Actually, we'll do 0, 0, 0 would be black because there's no color of it, no light. If you want to think about it that way. And 255, 255, 255 would be white. Okay. Does that make sense? Are there questions about that part? So we need to convert. Thank you for the thumbs up, Thomas. I appreciate that. So we need to convert RGB pixels so all three colors have the same value. Now we could, as I've specified it there, like if somebody came to you and said, take this picture and make it so that all the pixels, the RGBs have the same value. If that's all someone said, you could solve that problem by just saying, sure, I'll set them all to 0. They're all the same, right? That would satisfy this specification as it's phrased, but it wouldn't be very interesting because the picture would be black. And all pictures would turn out black. I'd hand you a picture of a unicorn, you'd give me a black picture. I'd hand you a picture of a smiling baby, you'd give me a black picture. I'd hand you a picture of a volcano erupting and you'd give me a black picture. Like everything would be black. That's all we'd ever get back. That would not be a very interesting program, right? Nobody would pay money for that filter in Photoshop. Not useful. So we need to do something more intelligent than that. And in particular, if we have a bright pixel in our picture, maybe it's a real bright green, we'd like that to be a lighter shade of gray than a real dark pixel. So if there's like, say, a really dark blue in our picture, we wouldn't want that to be a real light gray. We'd want that to be a dark gray. So like the dark green of my shirt should turn out to be darker shades of gray. A lighter area, say in my beard, where I've gone very gray, would be a lighter shade of gray in the pixel, in the final picture. So we want there to be a relationship between the brightness of the original pixel, and the new grayscale pixel, okay? And we're going to do that using what's called luminescence. So the luminescence, we'll say the average luminescence of a pixel is the average of its red, green, and blue values. And we'll use that as our grayscale value. So if we take the average of the red, green, and blue and it's pretty high, say it's 200, then we'll use 200 as the value for all of red, green, and blue, and that'll give us a pretty light gray pixel. If the average luminescence of the original pixel is fairly low, like 50, we'll use 50 for all of red, green, and blue, and that'll give us a fairly dark gray, okay? Questions about all of that setup? Okay. So let's actually write the program. So we're going to write a program, a function called grayscale. It's going to take a picture as an input. Now we're going to have to do this to every pixel in the picture. The original image is going to have all kinds of color in it, and we need to make sure every pixel becomes gray. We don't want some of the pixels to be converted to gray. We want all of the pixels to be converted to gray. And so actually it might be kind of interesting to do something where only some of the pixels are converted to gray. We can talk about that. But let's start out with all of the pixels are converted to gray. So whenever we want to do the same thing to everything in a collection, for loop for the win. So we have for something in something, right? That's the general pattern of a for loop. And the second something is the set of things we want to loop over. And when we're doing images, this is always going to be get pixels of picture. So that get pixels is a built-in Jest thing, not a Python thing. It's a Jest thing. And we give get pixels a picture, and it gives us a collection of all of the pixels back. So if the picture is like 400 by 600, that's 240,000 pixels. So this is a collection of 240,000 pixels. And we're going to go through and do something to every single one of them. Okay. Does that make sense? Questions about that? Okay. Now we need to give a name for each pixel. We could call it whatever we want. It's just a name so we can refer to that pixel when we're processing it. I will use the very exciting name pixel because it is descriptive. Okay. So this says for pixel and get pixels picture. So pixel will be the name of the first pixel, and then it'll be the name of the second pixel, and the third, and the fourth, and the fifth, and the sixth, off to the end. Okay. Now we want to compute the luminescence. I guess the book calls it intensity, so we'll use their word. So they say intensity equals get red pixel plus get green pixel plus get blue pixel divided by 3. So we're computing the average intensity of the 3 colors. So all we're doing is adding up 3 things and dividing by 3. So this is plain old simple averaging from like way back in the dim past. Okay. And now we're going to set the color. And there are 2 ways we can set the color of a pixel. One is we can set individual colors. So we could do this, and then we could repeat that 3 times for the green and the blue. Or we can do this in one spot. Actually, we can just say set color and hand it the pixel, and then we can hand it a color. And there's a function make color, and that's again a Jest thing. All the stuff about colors and pixels, those are specific to Jest. And we can say intensity, 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 boom, boom. So we're saying make a color where the intensities are the same. They're all whatever this value was. So this is guaranteed to be a grayscale color. Okay. And in fact, if it's easier to read, let's pull this out and say gray color. Boom, put that there. And then I can say gray color here. So now the 3 lines all do something specific. The first line computes the average, intensity of this pixel. And the second line creates a grayscale color with the average intensity. Can't type. And so the idea is that that color should have the same relative brightness as the original pixel. So if the original pixel was pretty bright, we should have a fairly bright gray. If the original pixel was pretty dark, we should have a pretty dark gray. It's kind of in the middle, we should have a kind of in the middle gray. And then we set the color to this new grayscale color. And then because this is the body of the for loop, when this finishes, goes back up to the for loop, moves on to the next pixel, does all this again. When that finishes, moves back up to the for loop, moves on to the next pixel, does all this again until all the pixels have been finished. Okay. So there's a lot there. Totally ask questions. I'm going to sit here and drink my tea for a second while you contemplate your navel and ask me questions. Yeah. Okay. I am launching a poll asking everybody to give me a sense of how well they feel like they understand this example. So vote away, peeps. Okay, everyone has voted. End poll. Share results. So, fairly well was the strong winner, but there are, you know, 2 people in Midland and 2 people that are a bit confused, which means we haven't like completely nailed it. Does anybody anywhere on this spectrum, not just the people in the middling and bit confused, but like all those people in fairly well, anybody have a question you want to ask? Some way, something that you're like, oh, I think I get this, but I'm not really sure. Or should we just keep going?
I got one. Like,
Okay.
do you need to divide by 3, or can you divide by like any number?
So that's a great question. Thank you. And who was that actually? I was looking the wrong way and I missed it. Who asked the nice question?
That was Thomas.
Oh, hi, Thomas. Thank you. So great question. So get red, get green, and get blue are all going to give you a number between 0 and 255. So in Jess land, reds, greens, and blues are all between 0 and 255. If we had just added it all up and not divided by something, we might have gotten a number that was like 700. And then when we put that back in, there's a problem because intensities are supposed to be between 0 and 255. So what happens if you put a 700 in there, right? So that actually creates some issues. And there's actually a settings that you can choose to change the behavior of Jess. But one is that anything above 255 is just treated as 255. And so if we didn't divide by 3, everything would get really bright and most of the picture would become white actually, because it would frequently be the case that the sum of red, green, and blue would be bigger than 255. And so a lot of the pixels would be white or very nearly white. You can also tell it to wrap around so that instead of going from just being 255 forever as you add things, 255 wraps around and becomes 0. And all of a sudden, you add 1 to the intensity and we go from pure white to pure black. And then you add 1 more and it would be a slightly less dark black and 1 more, a slightly less dark black. So then 700 would be like, it would wrap around several times and land probably somewhere in the middle. it'd be very hard to predict what would happen. So it's important that we divide by 3 here, at least for realism, right? I mean, this is one of the things with all of this image stuff is there are, what do you want? What do you need to do if you want like a realistic image? What do you want? But there are a lot of things you might do because you like the effect, like it has an artistic effect, an aesthetic effect that you think is cool, right? And so if we want realism, we need to divide by 3. If we want cool effect, yeah, we could divide by 2 or divide by 10 or multiply by 15, right? I mean, we can do a lot of weird things. Multiply by -1. We'd have to have the wrapping turned on for those things to do useful stuff. But if we want like our effects, we can do a lot of things that don't make sense. But if we're going for kind of a realistic grayscale image, we have to divide by 3 to move the sum back down into the range 0 to 255. And so if we take the average, it's guaranteed to be between 0 and 255, and that would be thumbs up and awesome. So does that make sense? Did that answer the right question?
Yeah, I just asked that question because when you add up all the pixels and you divide it by 3, it gives you back 255. So I assumed that would make the picture like more white than gray.
No, actually, it wouldn't give you 255. It would only give you 255 if all 3 of them started out as 255, if you divide by 3. So
Okay.
let's say they're all 100, okay? Then we would have 100 plus 100 plus 100. That's 300. We divide by 3, we're back at 100 again, right?
Mm-hmm.
Or if red was 50, green was 100, and blue was 150, we'd add those up and we would get 50 plus 100 is 150, plus another 150 is 300, divide by 3, and we would have 100. So if we had, if we started with 50, 100, 150, then we would have 50 plus 100 plus 150 divided by 3, which is 300 divided by 3, which is 100. So the intensity we would get for a pixel with this color, if we divide by 3, is going to just be 100. Whereas if we forgot to divide by 3, we'd have 300. We'd really blow it out, and we would get lots of super white.
Okay.
Does that make sense?
Yep.
Cool. Other questions? And actually, we could do an example quick because it's super easy to see what happens if we don't divide by 3. Okay, so if we have this, other questions about this? So let's do, we'll do the mass picture. Make picture, pick a file. And then we can say grayscale. Oh, I guess it would be useful to show the picture. And again, I have to play this game of sharing different screen. So that's the original mass picture. And now we'll grayscale that puppy and grayscale masks. Takes a second because there's a lot of pixels we got to process. Show mask. And now we'll share that. And there we go. Pretty good black and white version of the picture. Okay. And it's managed to maintain the relative brightness of the different sections of the picture. The window back here was very bright before. It's still very bright. This section of these masks were, like this is more in shadow in the bottom right, so it's definitely darker. This hanger was, coat hanger was darker than say this one in the original and it's darker in the black and white. So, you know, we got a pretty good black and white. Now, whether this picture's as interesting in black and white, well, probably not, to be honest with you. The color was part of what made that picture kind of cool. And so black and white, I think it's not as interesting a picture, but whatever, right? It did work, right? We were able to do black and white. So let's go back to Jess. So questions about that? And let's, for fun, let's try Thomas's thing of forgetting to divide by 3 and see what happens. So we'll load the program. We will reload my mass picture. We will grayscale it. We will show it. And then I will reshare. And you can see it's a lot more blown out. Many of the pixels went to pure white. And all of the pixels are brighter. So this, again, this section on the bottom right had been fairly dark before, but because we didn't divide by 3, everything got quite a lot brighter. This section in this mass with the overlapping circles got a lot brighter than it had been before. And there are a lot of like pure white pixels where there were not, like this section in here, we can see there are these pure white pixels in what was sort of a red area. And this mask over here on the left has become almost completely white. So forget, oh, and actually this coat hanger has almost completely disappeared because almost all of this coat hanger became completely white. So by forgetting to divide by 3, we made things much, much brighter. Does that make sense? Questions? So, actually, oh, let me, because I'm not sure you can see this. Let me go back and share. Actually, let me, oh, stop it, computer. Preferences. And now can I share that? Or is that part of? Oh yeah, it is, okay. So here's the preferences box for Jess. And normally you have no real reason to come in here and do anything, but you're always welcome to. But one of the options is this modulo pixel color value by 256. And that says to do the wraparound thing. And so if we turn that on and we say done, and then I re-display the picture. Do I have to rerun the program, or do I just have to re-display the picture? Oh, I think I have to rerun the program. So I'm going to rerun the program. So let me share Jess so that you can see something about what's going on. So I'm going to reload and rerun the program. I'm going to show, and then I'm going to, stop that sharing and share the new picture. So this is what happens if we don't divide by 3 and you have the wrap option turned on. Things sort of move around in weird ways, and areas that were pretty dark become lighter, and areas that were lighter become pretty dark. It's kind of random as to what happens. And the picture clearly does not look realistic in any sense. Like there's some very odd stuff going on. But maybe you like that. Again, like for an artistic effect, maybe you think that's awesome. that's really a decision that you would make as a creator, not a programming question, right? As from a programming perspective, you want to understand why that happens so that you can use it to your advantage if you want it. But whether you want it or not is really an aesthetic question, not a scientific question, right? Questions? Going. Okay. Then let's run back to Jess. Share Jess. And let's get to sepia here. So I'm actually going to put the 3 back. And actually, I'm going to quick without talking about it a great deal because I want us to be able to get to some other things. They have a second version of this right below in the book. And the main thing that they're doing here is it turns out that the human eye isn't equally sensitive to red, green, and blue. And so to get a realistic grayscale, it's better if you balance things a little differently than 1/3, 1/3, 1/3. And so they have new red equals get red pixel times 0.299. So they're kind of dialing back the red a little. Instead of having 0.3333 for a third, they're like basically 0.3. So they'll use a little less than a third red because the human eye is more sensitive to blue, if I remember correctly. Doing this right? Oh no, we're less sensitive to blue. We're more sensitive to red. So we're dialing back the effect of the red because we're already more sensitive to it. And then we've got new green. Get green pixel times 0.587. So we're kind of cranking up the green because we're not as good at recognizing green. And new blue, get blue pixel times 0.14. So we're saying pump up the green some and dial back the red and the blue, and that'll give us a more realistic human experience. And so then the intensity, if we wouldn't be average anymore, but if we stick to the form that we had before, we would have new red plus new green plus new blue. So we'd add those together, weighted intensity. So that should say pump up the green, but dial back the red and the blue, the impact of red and blue a little bit. And this is actually the fact that we have this perception difference is actually reflected in how the sensors in your cell phone's camera is constructed, for example. So there actually are sensors in your camera that are sensitive to red, sensitive to green, and sensitive to blue. And it turns out there are twice as many green sensors as red and blue sensors to get this balance right. So they actually build that into the sensor of the camera because of this way that your eye perceives light in the world. So this should give us, and actually it won't be a hugely different version of the picture, but we should get a slightly different version of the picture now. Let's see, grayscale new. Show mass share share. So that we don't have the other one to compare next to it, but it's if you put them both up next to each other, I suspect you'd be able to see that they're a little different, but it's not a huge difference. But if you care about like realism, this gives you a slightly better image. So questions about any of that before we do the sepia thing? Gone through a lot in a hurry. Oops, sorry, didn't mean to scroll away. Okay, then let us contemplate sepia tones. Page 121, make sure I'm in the right place. Yeah. So you've probably seen sepia tone pictures. If you Google sepia tone, you should find billions of them. And it was a particular, instead of pure black and white, there were certain chemical processes that had a slight yellowish brownish tint to them. And so some old photographs from, say, the 18 and early 1900s have this kind of slightly yellowy brown hue to them, which has come to be called sepia tint. And people tend to associate it with old-fashioned pictures. And so often there is an effect available in most photo systems where you can apply a sepia tint, which does two things. It makes your picture black and white, and then it adds this sepia tone to it, so that it feels kind of old-timey, whatever that means, right? And so they provide a program in chapter 5, program 51, that sepia tints a picture. And it does this by first converting it to grayscale, and then it loops through, it has a bunch of, it loops through the pixels again, and then it has a bunch of if statements that treat different parts of the picture in different ways. So brighter parts of the picture have more red added to them, and darker parts of the picture are left more just sort of straight up black, okay? So let's walk through that, because there's a couple of cool things going on here. So sepia tint picture. So the first thing we do is we convert to grayscale. And we could just repeat all of this, but one of the really important ideas in programming is you don't want to repeat yourself if you can help it. Repeated logic is one of the great sources of trouble in computer science. If we repeat something, we increase the burden of like understanding and modifying things later. And if an error is found somewhere, if we've repeated the code that contains that error many times, we have to find all the places where that got repeated and make sure we change all of them, fix all of them, or just update all of them. Maybe it's not a problem we're fixing, but a new feature we're adding. So like if we had the old grayscale and we had copied this for loop like 1,000 times in our Photoshop app, and then later on somebody came to us and said, oh man, don't you know, like the human eye does weird stuff, and you really ought to use this algorithm for computing grayscale because you'll get more realistic results. We'd be like, oh, totally should do that. That would be a great feature to add for version 3. But then we'd have to find all the places that we had put this and replace all of them with the new code. And if we miss one, that could be bad. So we would be sad about that. So instead, we want to reuse things instead of copying and pasting them whenever possible. So in this instance, we could just copy all this, but we don't want to. We just want to call it. We just want to use this to convert our picture to grayscale. So this is actually a really, really important point. So definitely be like, whoa, questions about this. But in general, you don't want to copy something if you can reuse it. And one of the great values of defining functions is that they give us little packages that we can reuse whenever we want. So we can build up a set of tools that allows us to reuse something. Questions about that? Okay. Now, you do have to have this definition. So if you like tried typing the definition of sepia tint in from the book and just running it without this grayscale new, or mine's slightly different than the one in the book, it doesn't matter, but you'd have to have a function called grayscale new. And if you didn't, this line is going to give you an error when you try to run the program. You'll get all kinds of shouty stuff. So you've got to make sure you have the functions that you're referring to, but if you do, you're good. Okay? Does that make sense? Questions? Okay, now we've converted it to grayscale. So we want to tint each pixel. And the fact that we're saying each here says, well, we probably want to get all the pixels in the picture and loop over them because that's what we do all the time. And so in the book's solution, basically they're adding a little red and blue to the pictures to get the color tones that they want. So they start off by saying red is get red from the pixel, and blue is get blue from the pixel. And then they just have a bunch of if statements. So if, oh, actually we could do this. Tint shadows. So if the red is less than 63, oh, I didn't need the parentheses. Too many programs. If red is less than 63, we're using that as a proxy here for it's a pretty dark pixel. Now the blue or the green could be higher, and it might be not as dark, but we're saying there's certainly very little red in this pixel. And so if there's not much red in the pixel, we want to increase the amount of red in the pixel by not a lot. 1.1, we're adding 10% red to the pixel. And we're going to dial back the blue a little bit. And that keeps the luminosity, the intensity of the pixel about the same. It's not quite equal. It's going to be a little brighter than it was before. The 0.9 on the blue doesn't remove quite as much as the 0.1 on the red, probably on average, but it's going to be really close. So we're saying, you know, if we've got the red, green, blue sliders, we're saying we're going to lift the red slider a little bit and lower the blue slider a little bit. And so the overall effect on the intensity is it'll be about the same intensity, but it'll be a little redder and a little less blue. Okay. Does that make sense? Questions? Okay. Then we will tint the highlights. So we're saying here, oh, the midtones are next, actually. Sorry. So we're looking for values of red that are kind of in the middle. And red less than 192. Oops, that should have been greater than 62. So we're saying if the red is bigger than 62 and less than 192, then we will do something. Now, looking at this, They got, I would argue they got their ranges kind of messed up, because red less than 63 includes 62 as a value. Oh no, but that's okay, because we're saying here this is 63 and up. Okay, I'm fine. Getting ends of ranges can be kind of tricky. I would actually have written this probably as red less than or equal to 62, and then here yeah, something like that. And then it would have been clear that this is less than or equal to 62 and this is strictly greater than 62. But don't need to worry about that too much. So on the midtones, we're going to actually amp up the red even more. So we'll say red gets red times 1.15. And then we drop the blue a little more to keep the intensity around the same, right? We're trying to not make the pixel go lighter or darker than it would have been. So this says add some red, but subtract roughly similar amounts of blue, so the intensity of the image stays about the same. And then the last one is to tint highlights. If red greater than or equal to 192, red gets red times 1.08. So this is a little less pumping up than we had in the shadows. And they're worried about red possibly going over the top here. So if red goes over 255, we'll drop it back down to 255. So you sometimes will see things like this as a way of saying, hey, if we've gone off this chart, let's dial it back so it's at the top. Similarly, if we were subtracting color, we could be like, oh, if we went below 0, let's bring it back up to 0 to make sure that we're not off the scale. And then blue gets blue times 0.93. And then that long set of things, all of this business gives us new values of red and blue. But those are just variables in the function. We haven't actually applied them to a pixel yet. And until we apply them to a pixel, we haven't changed the picture any. Okay, so we now need to apply these to the picture. So we will do that by saying set red pixel red and set blue pixel blue. And we've never changed the green. We've left the green alone. We've only modified the red and the blue. And that should do the job. So we convert the picture to grayscale. Then we go through every pixel and we get the red and the blue, and we modify the red and the blue according to these rather bizarre rules. And the book says, like, these numbers are just them fiddling around. Like, they played with it until they thought it looked nice. And that happens a lot with these kinds of things. Sometimes there's like real physics and you've got to make it like just this way. But a lot of times it's like fiddle with the numbers until it looks the way you want it to look, until it looks pretty. Okay. So questions about this before we try running it? There's a lot going on there. Feel free to ask. Going. Okay, load program. And then let's apply this to, let's apply this to a different picture. Let's do the gate picture. So let's try this one. And let's show that picture so we remember what that looks like. Stop sharing, share, ba-doom. Okay, so this is the picture we're going to apply this to, and we'll see what happens. And actually first, let's look at this in grayscale so we know what the grayscale version looks like, and then we'll apply the sepia thing to it. So grayscale new gate. Show gate. And let's share that. And that's a fine picture. I don't think it's great in grayscale. I think it's much more interesting in color, but you know, there we are. It's a grayscale version of the picture. So let's actually try applying the sepia thing to it and see what we get. So share Jess, you know. So let's reload it because we've got the grayscale version and we want the color version to start with. And then we're going to call, what did I call the program? Sepia tint. 8. Finished. Show gate. And then we'll share that so you can see it. That would be more fun. Voila. And there we have a fairly sepia tinted picture. So, you know, it did its thing. This isn't perfect in a couple of ways. And this picture actually really shows up one of the weaknesses of the approach that we took. A different picture that didn't have a broad expanse of sky like this probably wouldn't have shown this feature up, but we had that big batch of blue sky, so it did. You can see, I think, that there's kind of a weird edge right here where I'm going over with my mouse. Is that visible at home? That there's sort of a strange jump from a brighter orange to a duller color. Okay, cool. So that's the if statements. So this is probably in the highlights section, and this is probably in the midtones section. And because there's like an edge, we can actually see when it jumps from one treatment to another treatment. We get this weird artifact here. And so, you know, if you really wanted it to look more natural, you'd want something that blended more smoothly instead of having just 3 sections, and which gives you the possibility of fairly big jumps from one treatment to another. There's also, I think, an edge here between what I'm guessing is the shadow section and the mid-tone section here. And you can see there's a bit of an edge. It's less noticeable because it looks like it might just be sort of a trick of the light that would create that spacing. Whereas here in the sky, it's pretty obvious that something's up. And that's because we've just got these 3 categories. And if we had a slightly more subtle approach, we could get this to smooth out, but it would make the code a lot more complicated. So we're gonna not worry about that right now. Okay, so yeah, we did a thing. Let's try tinting one other picture just for fun. Let's do the tree. and we'll sepia tint tree, show tree, and then we'll share so you can see. So that was actually pretty cool. I think that's actually a nice effect on this one. There's still some banding artifacts in the sky reflected in the water, especially down here on the bottom right. But in general, there's the patches of color are broken up enough in this picture that those artifacts aren't really visible. And I think that actually makes for a very nice effect on this picture, which is interesting because part of the reason I like the picture is the color in the trees and in the water, and this removes that, but I still think that's actually a very cool effect. So yay us. Okay. Questions. It is 10:14. I was going to have you go do something now, and we're kind of out of time for that. So I'd really love to have, in the next 6 minutes, some questions. I'd love to have some feedback on things people are confused about, things people would like to see again, have explained again. Tell me a story.
I have a question.
Go for it.
So how does set media path work?
Oh, okay. Let me I'm gonna pop up a poll about the sepia example, and while you're answering that, I can talk about set media path. If I want to, let's say I want to say gate equals make picture Japanese gate.jpg. That fails because it's like, whoa, there's no picture there. And there's no file with that name there, actually, is really what it's saying. And the question is, where is it looking when you ask it to do something like make picture file name? Where does it actually look for that file? And one advantage of pick a file is we can go here, and we can tell it exactly which file and exactly where we want to go. But sometimes we want to be able to do things like just provide a file name, because maybe we want it to be part of a program that's pulling some specific pictures to make a collage, for example. And so we need to have a way of telling Jess, here's where we want you to go look for stuff. And so set media path allows us to do that. So let's see, actually, if we help set media path. So if we pull up the help for that, and so I did that. I don't think you could see the menus, but I went up to the help menu, which on a Mac is up in the menu bar. On Windows, I think it's in the Jess window. And there's a search thing there, and you can go search for particular functions you'd like to understand better. And so we can say set media path, and we can give it a path to a place, and it will go there, and any subsequent references to a file will be to this file in this location that was specified by set media path. So you can use that to say, in what follows, I want you to always go here. So if I didn't want to keep doing pick a file, but I wanted to be able to do things like Japanese gate, right? I could say set media path, let's do it this way first. Now, you don't get to see the thing that pops up, I think. Is that true? Are you just looking at the regular Jess thing, or are you looking at a choose media path box?
We get a choose media path box.
Oh, you do? Oh, awesome. Thank you. So I can then use this to specify where I want to go looking. And here, I'm just going to go ahead. Oh, actually, I have to back up one because you have to choose a directory, or a folder. So I'm going to select my images and say choose. And so it's going to use users, McPhee, CSci 1201, F20, my images. And now if I say gate, that works because it looks in this folder for this file and it finds it. And so now I could say show gate, and you get to see the original gate. I mean, you can't see it because Zoom's sharing the wrong thing, but it did actually bring up the correct gate picture. So that you can use that to sort of say, that's where I want things to come from or be saved to. If you want to save an image, set media path is useful so you can find the picture later. Because otherwise, if you save an image, who knows where it went to? The set media path allows you to say, I want to read pictures and sounds and other things later on from this folder. And when I save them, I want them to go to this folder so I can find them later. Does that make sense? Questions about that? Did that help?
Yeah, that did. Thank you.
Cool. Okay, so we're 1 minute after. We should wrap up. The poll suggests that most people have some like okayness with the sepia example. That's good. That makes me happy. If you're in the kind of confused category, especially, I would definitely like set up an appointment slot. I think there's a bunch of unused appointment slots today still. Yeah, there's actually like a ton of them today. So, grab one or send me an email or ask a question on Slack or whatever, and I will try to help out. Otherwise, go play with this stuff. I'm actually going to post a little assignment where I'm going to ask you to just make a picture with Jess. Do something with Jess. Make it grayscale, make sepia, do something funky that you like using either an image of your own or an image you get from somewhere, but do something with Jess and share it so that we can all see, and it'll be like shared in a public discussion so everybody in the class will see it. So, behave. But I'd like to make sure everybody can like make a picture that has something changed about it. And I don't really care what. I'm just like, show me that you can fiddle with a picture, and we'll have that due like Monday evening just to make sure everybody can do something. Okay. So I will let you go. Thank you for your time and attention. Have a good weekend, and I will see everybody later. Cool. Out of here. Pew.